Scene: animated view of a retaining wall holding back soil with earth pressure arrows. Hello, welcome back to Civil Engineering Edge. Now dive into complete counterfort retaining wall design, step-by-step civil engineering guide. In the world of civil engineering, retaining walls are crucial for stabilizing soil and creating level surfaces on sloped terrain. Among the various types, counterfort retaining walls stand out for their efficiency in supporting high earth pressure economically. So, what exactly is a counterfort retaining wall? A counterfort retaining wall is a reinforced concrete wall used to retain earth or other materials at different elevations. It consists of a vertical stem or face, a heel slab under the retained earth, a toe slab projecting on the other side, and counterforts thin, triangular vertical beams or ribs spaced at regular intervals along the back of the wall. These counterforts act as tension ties, connecting the stem and base slab to resist bending moments. Instead of acting as a simple cantilever wall, the stem and heel behave as a continuous slab, supported by these counterforts, thereby reducing the thickness and reinforcement required. Cut to animation showing the structural load path and earth pressure distribution. This design becomes particularly beneficial for heights over 6 meters, where cantilever walls become uneconomical. The inclusion of counterforts allows for thinner stem sections and more distributed loads, which significantly reduce the internal moments and shear forces acting on the wall. In this video, we will walk you through the step-by-step design process of each part stem, heel slab, toe slab, counterforts, and ties, followed by the benefits and cost-effectiveness of using a counterfort retaining wall. Let's begin the design process. Design of stem. Scene: cross-section of the wall stem, showing pressure diagram and reinforcement. The stem of a counterfort retaining wall resists lateral earth pressure from the retained soil. Since pressure increases linearly with depth, the maximum moment occurs at the base. The stem acts like a vertical slab supported horizontally by counterforts. The lateral earth pressure P is calculated using Rankine or Coulomb theory. P equals 1/2 times K times gamma times H squared, where K equals earth pressure coefficient, gamma equals unit weight of backfill, H equals height of the wall. Once P is known, calculate the maximum bending moment max and design the stem as a continuous slab between counterforts. The spacing between counterforts is usually 2 to 3 meters. The thickness of the stem varies, thicker at the bottom approximately 300 millimeters and tapers to the top approximately 150 millimeters. Reinforcement is provided mainly at the rear face tension zone and placed horizontally and vertically as per calculated bending and shear forces. Adequate cover 25 millimeters is provided, and the stem is also checked for crack width, deflection, and durability per IS 456 guidelines. Design of heel slab. Scene: bottom slab highlighted with load arrows from soil and wall. Narration: the heel slab lies beneath the backfill soil and experiences both soil pressure from above and uplift from below due to bearing pressure distribution. The slab acts as a cantilever slab fixed at the wall base, projecting backward. The design load includes self-weight of the slab, soil weight gamma times thickness of backfill, surcharge load if applicable. Uplift pressure is considered from the soil bearing capacity and groundwater if present. Net pressure is calculated, and the maximum moment M is evaluated using M equals W times L squared to 4 cantilever slab. Here, W equals net load and L equals heel projection. Design the slab for bending using AST equals M 0.87 times Fy times D. Minimum reinforcement must be ensured as per his code. The slab thickness is usually around 200 to 300 millimeters, and tension steel is placed at the bottom face. Proper anchorage at the junction with the stem ensures monolithic action and avoids punching shear. Drainage pipes or weep holes must be provided in the heel zone to relieve hydrostatic pressure. Design of toe slab. Scene. Animation showing toe slab resisting uplift and bearing load. The toe slab projects in front of the wall and helps balance the wall by resisting overturning moments. It primarily experiences downward bearing pressure from the superstructure and upward soil reaction. Designed as a cantilever slab projecting from the base of the stem, it must be checked for bending moment, shear stress, bearing pressure. Design load on the toe includes self-weight, reaction from the wall, possible surcharge if any. The net pressure distribution under the base is determined from eccentricity due to overturning moments. The pressure diagram may be trapezoidal or triangular. The bending moment at the fixed edge is calculated using M equals W times L squared, 2. The slab thickness is generally 150 to 250 millimeters, and reinforcement is placed at the bottom tension zone. Toe slab design is crucial for the stability of the entire retaining wall. It helps reduce overturning and provides resistance against sliding by increasing the base area. Proper reinforcement anchorage and detailing ensure structural safety and long-term performance. Design of counterforts. Scene. Internal 3D view of counterfort ribs behind the stem. Counterforts are inclined or vertical reinforced concrete ribs that connect the stem to the base slab and act as tension ties, reducing bending moments in the stem and heel. These are placed 2 to 3 meters apart along the back of the wall and extend from the top of the stem to the end of the heel. They are designed as triangular vertical beams, fixed at both ends. Top fixed to the stem, bottom fixed to the base slab. The counterfort resists bending and axial tension, with critical load coming from the lateral earth pressure transferred from the stem. The bending moment and shear force are computed considering the pressure from the retained earth acting perpendicular to the stem. The cross-sectional area of the counterfort is designed for both flexural and shear capacity. Typical reinforcement includes main bars along the length vertical direction, stirrups or ties across width. Proper anchorage and development length are essential to ensure composite action. They help make the wall more economical, especially at greater heights, as they allow for reduced thickness of other components like the stem and heel. Design of ties. Scene. Reinforcement detailing showing horizontal ties between counterforts and stem. Ties are reinforcement elements used to connect the stem and counterforts, ensuring monolithic action and preventing relative movement between the wall parts. They primarily resist tensile forces generated due to differential earth pressure and distribute loads between components. In counterfort retaining walls, ties are typically horizontal steel bars placed near the base and middle height of the wall, welded or lapped with the main reinforcement. The design involves calculating the tensile force expected in the joint section and then using AST equals T, 0.87 times phi, where T is the design tensile force, phi is the yield strength of reinforcement, and AST is the area of steel required. Ties must be spaced adequately to control crack width and ensure even load transfer. Additionally, ties must be properly detailed at junctions with bends, hooks, or welded joints to resist pull-out forces. In taller walls, multiple layers of ties may be used at varying heights for better stability. These small but critical elements greatly enhance the wall's durability and performance under extreme loads. Benefits, cost effectiveness, and conclusion. Scene. Time-lapse of retaining wall construction followed by 3D cost comparison. Counterfort retaining walls offer multiple engineering and economic benefits. By introducing counterforts, bending moments in the stem and heel slab are significantly reduced, enabling the use of thinner sections and less reinforcement. This results in material savings, especially in large-scale or tall walls, making it highly cost-effective compared to a massive gravity wall or even a plain cantilever wall beyond 6 meters height. Some key benefits include reduced concrete and steel usage, better load distribution, greater structural stability for tall walls, faster construction due to modularity. The initial planning and formwork may be complex, but the long-term savings in material and maintenance outweigh the costs. Moreover, counterfort walls adapt well to terraced or hilly terrain, making them ideal for highways, bridges, and industrial sites. Conclusion: the counterfort retaining wall is an elegant blend of structural mechanics and economic efficiency. With proper design of the stem, base slab, counterforts, and ties, it ensures safety, longevity, and value. Animated full wall with labels on each part. Thanks for watching. Don't forget to like, subscribe, and share this video to Civil Engineering Edge for more insightful civil engineering content.